Okay, so welcome to the One World Mathematical Physics seminar. This seminar is organized by the International Association of Mathematical Physics and takes place every 2 weeks online. In case this is the first time you are joining us, you are very welcome to go and visit the webpage of the association. So today's speaker is Andreas Deuchert from Virginia Tech, and he's going to talk about the Gibbs state of the mean field Bose gas.
Okay.
So I let you speak.
Well, thank you very much for the introduction. Also, thank you very much for the invitation. It's a pleasure to be here, and I'm very much looking forward to presenting this work. So this is actually joint work with Fanta Nam in Munich and Marcin Napiorkowski in Warsaw. And it has been a quite long project. So there are many new ideas, and I'm trying to convey some of them. Okay. And if you have questions, please ask right away. So I prefer that. I would really like you to understand. It's not like I want to brush through it. So if there are any questions, please ask. I'm happy to explain more at every point. All right, so it will be about the Gibbs state of the mean field Bose gas. And before I introduce the model, let me give some brief introduction because, well, just that we're all on the same page. Good, so I'm going to talk about a gas of bosons. So this here is a gas for me. The wiggly lines are there because it's quantum mechanics. So it's quantum mechanical particles that have a wavelength in a way. Okay, so we have waves and particles. Now, it's about the Bose gas, and the Bose gas displays a phase transition. And let me start by quoting Wolfgang Keitel, the winner of the 2001 Nobel Prize in Physics. He says Bose-Einstein condensation is one of the most intriguing phenomena predicted by quantum statistical mechanics. So that should suffice as motivation. So what is Bose-Einstein condensation? Well, it's a phenomenon where below a certain critical temperature, a macroscopic fraction of all particles starts to do exactly the same thing. And this exactly the same thing has to be taken literally. So you can see this in experiments. You can probe this property. And how does it look like when you test it in experiments? Well, let's have a look at that picture here on the left. So what you see are 3 snapshots of the velocity or momentum distribution of a gas of particles. And from the left to the right, the temperature is decreased. And well, that blue peak that emerges in the middle below the critical temperature Tc, that's a peak in the momentum distribution. So that's the macroscopic fraction of all particles that condense into a state close to zero momentum or velocity. Now, this happens in non-interacting and in interacting system. And because of this, the Bose gas displays a wealth of interesting phenomena, which are all related to this phase transition or the presence of the condensed phase. And they are all notoriously difficult to study mathematically, mainly because of 2 reasons. First, we have a curse of dimensionality in the system. So the relevant Hilbert space grows exponentially in the particle number. And second, well, techniques from physics or many techniques from physics, like, for example, perturbation theory, don't work. Okay, so there's a small denominator problem. So why is this relevant? Well, because most of the intuition gained for these systems, are gained with these techniques. Okay, and if you want to study these phenomena mathematically, you necessarily have to come up with new mathematical techniques. And this is why these systems are so interesting from a also purely mathematical point of view. Now, here's another picture. Well, here's our picture again from the gas. That is for me a gas above the critical point. So we have quantum mechanical particles. We see the quantum mechanical nature, but we don't see the the Bose-Einstein condensate yet. Now, if I lower the temperature, that is a more accurate picture. So above that giant matter wave, which represents the condensate, you still have individual particles. And if you lower the temperature further, then you come to an almost fully condensed state. And what the system or the parameter regime I will be interested in is basically all of it. But for the purpose of that talk, think about that parameter regime, okay? So we have a condensate, we have a macroscopic number of particles that do exactly the same thing, but we also have a macroscopic number of particles outside the Bose-Einstein condensate. So think half of the particles are inside the condensate and half of the particles are outside. All right. And what is the mathematical description of the system? Well, it's in terms of quantum mechanics, and in particular, it will be in terms of a system that is that allows for particle number fluctuations. So, in other words, I will be interested in the grand canonical model. Okay, so there can be fluctuations of the particle number, and for the sake of simplicity, I will consider particles on the unit torus. So this is just to make to avoid mathematical problems that will not be hard in the end. So we leave them away. So we are on the unit torus, and so the one particle Hilbert space of the system is just L2 of functions on the three-dimensional unit torus. And the Hilbert space of the entire system is the bosonic Fock space. So that's just the direct sum of all the n-particle Hilbert spaces, where, well, the n-particle Hilbert space is an L2 space of symmetric functions. So that's crucial here. It's really, so if you look at that line here, the functions we consider are square integrable, and if you exchange two arbitrary particle coordinates, the function stays the same. So it's a completely symmetric function. This implements the fact that we're dealing with bosons, and it has far-reaching mathematical consequences, as, for example, the existence of the BC phase transition. Now, the Hamiltonian I will be interested in is the following. So let's look here. That's in the n-particle sector. Small n is now the particle number. We have a sum of Laplacians. This is the kinetic term. And we have an interaction potential, V of xi minus xj. That's a multiplication operator. And the point is somehow we have, if you just think of this capital N and the small n being the same, if they were the same, well, the 1 over n would balance the two terms, okay? We have n terms here and we have n squared terms here, so this is balancing the two terms. But it's actually, from a physics point of view, it's doing more. If you think about the length scales, so we have the unit torus, so length scale 1. Now, the interaction potential also lives on length scale 1. So many particles interact with each other, right? We have n particles on a unit torus, so the typical distance between them is n to the minus 1/3. And so this is a mean field interaction. Order n particles interact with order n particles, okay? Or one particle interacts with order 1 particles. So this is a mean field model, okay? And the small n and the capital N are actually not the same, but what we will do is we will choose the expected number of particles in the system to be capital N. So whenever you see a capital N in this talk, it will be the expected number of particles in the system. And then this still implements a mean field scaling simply because the variance of the particle number will be such that the distribution is peaked. Okay, so the variance, I will talk about the variance later, but it will be much smaller than n squared. So we have a peaked distribution, and because of this, this makes sense. Now, this is a mean field model. Mean field models are not the physically most realistic ones, but they are still, they turn out to be mathematically rich in the case of bosons, and they have a second advantage. So there are several models which are probably physically more realistic, like dilute Bose gases. And it turns out that, well, for these models, if you can prove something for a mean field model, there is hope to prove something for a more general model too. And I'm just looking, there's no question in the chat so far. Okay, let me close this. Okay, so this is a toy model, but the techniques we develop, you would expect they apply with modifications also to other models, in particular to physically more realistic models. Okay, so what are the quantities we will be interested in? So, no, wait. First I have to introduce some more language because I will need it actually quite a bit. And these are the creation and annihilation operators on Fock space. So most of you, or many of you will know it, so I do it rather quickly. But if you have questions, please ask. So the creation and annihilation operators are natural algebra of operators on the bosonic Fock space, and they do what their name says. So they create or annihilate a particle. So let's define it first and then say why it's nice. Well, what you do is really the A star of P is the adjoint of A, and it creates a particle. So what you do is you take an n particle wave function, this is that guy here, then you just multiply it with phi p, where phi p is just a plane wave, e to the IPX, and then you symmetrize that again. Okay, so there's a normalization factor here and a symmetrization. I won't talk about that. Okay, so but the message, it really creates a particle, and then the AP is the adjoint, and I don't write the formula, but it does the inverse of that operation, so it takes away a particle from the system. And these operators satisfy the canonical commutation relations. So AP, AQ star, so this is the commutator, the bracket here, is delta PQ, and all the other commutators vanish. And now it is very convenient to write the Hamiltonian in terms of these operators in Fourier space. Okay, so we have two terms here. Remember the first term, that was the Laplacian. So the Laplacian in Fourier space is just multiplication with p squared. And the AP star AP implements basically that sum here. Okay. Okay, also the interaction potential, you can express it in Fourier space in that form. And this is how it looks like. Okay, if you don't understand the details how I got here, so V hat of P is the Fourier transform of V, that's not important. So I will explain how I use it later. Okay, and we will later need that the Fourier coefficients of the interaction potential are non-negative, and this is natural for the problem. You will see that later too. All right, so let's talk about the quantities I will be interested in. So in the end, I will be interested in the Gibbs state, but the free energy is also relevant. So let me mention it at least. So I will be interested in equilibrium statistical mechanics. Okay, so we have a free energy, we have a Gibbs state, and the free energy reads like that here. So it's -1 over beta. Beta is the inverse temperature. The log of the trace of e to the minus beta, hn minus mu cal n, or calligraphic n. So that's the particle number operator. If it acts on a state with n particles, it gives you n. Okay. And plus mu n. So first of all, that part here is just the grand potential. I make it into a grand canonical version of the free energy by adding plus mu times n. This is just because I work in a formalism where I fix the expected number of particles and not the chemical potential, which is of course completely equivalent, but it's more convenient because of this mean field parameter here. Okay, I don't want to express that in terms of the chemical potential. That would be a bit unpleasant. So I prefer to fix the expected number of particles in the system, but nevertheless be grand canonical. And then this is the natural thermodynamic potential to work with. Now, this guy here satisfies a variational principle, which is not so relevant at the moment, but the unique minimizer of that is the grand canonical Gibbs state. Okay, that's this guy here. So it's the usual exponential of the Hamiltonian minus mu particle number operator. And I assume that the chemical potential will always be chosen such that, without mentioning it, always be chosen such that the expected number of particles equals to n. Okay, and this will be the main object I will be interested in. Now, what is the parameter regime? So there's a very natural parameter regime here as you let the particle number go to infinity, and that is you choose your inverse temperature on the scale of the critical temperature of the BC phase transition in the ideal gas. Okay, so that's a very natural temperature scale. And now you can look at what is this critical temperature of the ideal gas, and I will motivate that a little bit on the next slide. It scales, well, it is actually proportional to rho, the density, to the minus 2/3. But since we are on the unit torus, this is rho is the particle number. Okay, so the point is there's one free parameter in the system. This is, and we choose it. We choose a length equal to 1 because we can do it. We could also let the box go to infinity, I mean, make the box size large, then beta would not depend on n. But we find it more convenient to do it in this way. Okay, and I mean, we can, just to make this clear from the beginning, we can also treat the zero temperature limit, but in all my formulas, I will not display it. So, I mean, I always assume that beta is proportional, is equal to kappa beta c, and kappa is something fixed in the interval 0 infinity. So it doesn't depend on n. Okay, so let's talk a little bit about the ideal gas. So we're all on the same page. If we set V equal to 0, so there's no interaction, then we obtain an exactly solvable model. In that exactly solvable model, Bose-Einstein condensation occurs, and the particles that condensate into the one particle quantum state with zero velocity or zero momentum. And by N0 ID, I denote the expected number of particles in the Gibbs state in the condensate. Okay, so that's given by this expression here. But if you do, I mean, if you're not familiar with the A0 star A0, just think it's really the expected number of particles in the condensate. Okay, so the number of particles in the condensate is a random variable. You can compute the expectation, and in particular, there's a law of large numbers. You can compute the asymptotics, and you find that it behaves like that here. So it's proportional to, as you let n go to infinity, to n times 1 minus beta c over beta to the power 3/2, the positive part. So that's only the leading order asymptotics. And here you see if you have beta larger than beta c, so that means t smaller than tc, you are in the condensed phase. If you have beta smaller than beta c, which is t larger than tc, you are in the non-condensed phase, and the phase transition happens at one definite point. And here is the critical temperature again. And as has been shown, and that comes in the next slide, this behavior persists in the interacting model. Okay, so for this kind of model, we can prove the BEC phase transition. All right, so here is some selected literature. What do we know about this model? And I will now freely jump from this Hamiltonian here without the direct sum and a fixed particle number and that grand canonical version. Okay. So what is known about that model? So first of all, from the paper of Seilinger in 2011, we know, well, first of all, that there's Bose-Einstein condensation in the ground state. I don't even know when this has been proved for the first time. Probably it has been proved for another model for the first time, and then it was clear that it also works here. This would be a proof due to Seilinger and Lieb from 2002. But So using this, so in the paper of Saringer from 2011, he proved that he made a statement about the low-lying excitation spectrum of the Hamiltonian with a fixed particle number. Okay, so what you can prove is that a Bogoliubov approximation works for that model. So this famous paper from Bogoliubov from 1947, if you do a C-number substitution for the model, we will talk about that in a second in detail, then you can come to, again, an exactly solvable model that still depends on the interaction. And while this model correctly predicts the excitation spectrum of the many-particle system in the limit n to infinity, so you can approximate that. Now, the next paper is an extension of that to more general models. So Seiringer's paper was for the gas on the torus. You can also do it for trapped systems, for example. And here in that last reference, in that line, Nam and Seiringer could also treat like where you condense into, well, you have fragmented condensation. So there's not only one condensate function, but several. Now, what about the BEC phase transition in this model as you vary temperature? Well, this has been proved for another model first, and this is actually harder in the first two references here. So the first reference concerns the trapped system, and the second reference concerns the system on the torus, the system on the torus. So this has been the first proofs of the BEC phase transition for realistic continuum models in what is called the Gross-Bedayevsky scaling. This is while you have a singular scaling, so the interaction converges to a point interaction. Okay, and that last reference here is a mean field model where we studied the dependence of the critical temperature on the interaction. Now, here are two very interesting works. This also concerns the grand canonical system at positive temperature. And here the authors, and the results are basically the same, but the techniques are very different. So what the authors proved here is they looked at, well, basically they approached the critical point from above, and then they tried to see, well, the emerging Bose-Einstein condensate. So, I mean, above a critical point, if you do that, you expect to see a quantum field theory, right? And what they see is, indeed, they see a classical field theory that can be justified as an effective theory for this model. I should point out that to see this, you need to scale the interaction slightly differently than we did. You need to ramp it up a little bit, okay, to see this effect. All right, so that's not what I will be interested in. So what I will be interested in is rather not zooming in at one point, but make a statement about the Gibbs state across the whole temperature range. And the accuracy we will have, or we will need to see that, is basically the same as in these two references down here. And well, we are ready now for the first theorem, and I will explain that very peacefully. So we come to the slide. There are many things to unpack, but don't be worried. I will take the time to do it. So if you don't understand something on this slide as I go on, please ask, because for me, that's the most important slide. I want you to understand this. So our goal is to understand the Gibbs state of the interacting model. And one way to do this is to derive an approximation. And what we do is we derive an approximation in trace norm. And that trace norm approximation will allow us to compute many, many quantities of that system. So it's like almost, it's like almost solving that system, if you like, okay? Well, so let me first explain how the Gibbs state approximately looks like, motivate why it looks like that, and then let me explain consequences and some mathematical techniques. So here is a reference state. we show that the Gibbs state is close to that reference state in trace norm. And how does it look like? Well, it has several ingredients. It's interesting because it's non-quasi-free. And let me explain how it looks like. So first, let's look at that part here. Let's only look at these two parts and completely forget about the integral. So we have one part describing the condensate. This is the ZZ projection. And we have one part describing the thermally excited particles. So how does the Bose-Einstein condensate look like? How does the ZZ part look like? Well, that's a state which only acts on the Fock space of the zero momentum mode, and it's described by a coherent state. Okay, a coherent state, here's the definition. A coherent state is often used to describe a grand canonical condensate, and how you should think about it is, well, it's peaked around its expectation. The expectation of the particle number in that state is going to be absolute value of z squared. And apart from that, it has a Poisson distribution. That means in particular that it's peaked around z squared. Okay, so it's an approximation of having z squared particles in the condensate, but with some natural fluctuations given by a Poisson distribution. Okay, so that's the Bose-Einstein condensate for now. Then we have a second part here, the G-Bog of Z. This is the Gibbs state of a Bogoliubov Hamiltonian. So it's the Gibbs state x minus beta h. And now I have to tell you what h is. Well, the Hamiltonian in this exponent, in the exponent, is that guy here. It depends also on z, and it looks like that. So we have a kinetic part, a kinetic term, and that kinetic term is exactly the same as before. So this is unchanged. And then the interaction enters the game, and it does so in a very precise form. So we have here n0 of beta n is, my notation is wrong. It should have an ID. It's the expected number of particles in the condensate of the non-interacting model. Okay, this is an approximation that can be justified. And we have this funny thing here. So it's 2 AP star AP, and then we have phases here. And this is something that comes from the C number substitution. So if you test the original Hamiltonian with that state, only that part here, you get many terms, and this is part of the terms. And let me explain this in more detail. Okay, I come back to that slide. So we can write the Hamiltonian like that here. This is just an identity. We have several terms. Here we have one term. This is the kinetic term. Here we have an interaction term. This, by the way, didn't show up there. In this model, it gives you a contribution, which is v hat of 0, n divided by 2. So this gives you a constant. This is a non-trivial statement, but it does. Then we have these terms here, and these terms, if you act with the coherent state has the property that if you act with A0 on it, you get a Z. Okay, so the coherent state is an eigenstate of the annihilation operator. It's not an eigenstate of the creation operator. So if you act with A0, let's look at this guy to the right on a Z, you get a Z squared. If you act with the A0 star to the left, you get a Z bar squared, okay? And those here give you a Z absolute value squared. Now, if we go back here, well, we see the right phases. We see the right phases, and well, that the Z squared, the absolute value squared, can be replaced by N0 of beta n, that's part of the theorem, okay? So it's you replace a random variable by its expectation. This is what we do, and it's part of the theorem. Now, here are several other terms. And, well, the point is, if you think of it, we have exponential to the minus beta hn, and we want to approximate it by something. Well, it basically means, that many terms here don't matter. And it's the main part of the theorem to prove that they don't matter in the exponent. And they don't matter because of two reasons. First, they could be such that they don't change the structure of the Gibbs state, but they are large. That's that term here. That term here doesn't change the structure of the Gibbs state. It can be approximated by a number and something related to the condensate that I explain in a second. So that term is large, it contributes, but it doesn't change the structure of the Gibbs state. Those terms here in the last two lines, they would change the structure of the Gibbs state. They are potentially very, very dangerous. And we have to prove that beta times these guys are small. So we can throw them away in our approximation. And that will be done with two new correlation inequalities that we proved. Okay, I will come back to that later. But now let's go back to that slide. So I hope you have now some feeling for the Bogoliubov Hamiltonian here. This is really giving you the structure of the Gibbs state. But there's something I missed so far, and that is this integral here. And the integral is so it's a convex combination. So by the way, this here is a quasi-free state. Now we kill the quasi-free property by taking this integral here. And that integral is an integral over a one-mode phi to the 4 theory, if you like. And here is the relevant distribution. And that distribution appeared recently in a paper that I wrote with Chiara Boccato and Stocker. So Stocker was a master student of mine, and Chiara Boccato is a professor in Milan. And we used it in a similar context to prove an upper bound. And this here can be viewed as a justification of that effective theory. So what we have here is, well, minus beta v hat of 0 over 2n. Okay, this is a coupling constant. And then we have z to the 4. And okay, minus the chemical potential, this is to get the right particle number. But the c to the 4, that is part of that term here. So if you think of u and v being 0, it's part of that sum, then you get a z to the 4 if you test in the coherent state. Okay, but here are more terms. Okay, they don't appear in the formula because they boil down to a constant 2. It's actually, the point is the expectation of that here in the Gibbs state is n squared. But what's important for us, also the variance of that here matters, and the variance enters effectively that guy here. All right, and while you don't see the variance structure here, you only see the z to the 4, but to get this, you need to understand the variance of the number of particles in the condensate. Okay, so that means also here are part of the interaction terms. And if you put it all together, you get this integral here, you get a convex combination of these quasi-free states here. And well, as I said, that state is not quasi-free, and it's not quasi-free for one main reason. So the Gibbs state that we started with commutes with a particle number operator. So it's block diagonal in Fock space because Hn does commute with a number operator. Now, if we want to approximate that state, we better approximate it by something that commutes with a number operator as well. That is also block diagonal in Fock space. Now, how do you do that? These states, I mean, I just told you this Z state has particle number fluctuations, the Gibbs state of the Bogoliubov Hamiltonian as well. So that is not a good approximation. Well, the point is, if we integrate here, because the GBC depends only on the absolute value of Z, we have phases. And those phases, they assure you that any expectation of creation and annihilation operators that you compute, I mean, let's make a simple example. A0, the expectation of A0, it's non-zero in that state, but what you get is the absolute, I mean, you get Z. This is what comes out. And then you integrate over G, and well, it only depends on the absolute value. So you integrate over all phases and you get 0. So this is the way how this integral makes the state particle number conserving. Okay, and this is also why it's not quasi-free. In fact, all expectations with an even number of creation and annihilation operators almost looks quasi-free. There's something related to this phi to the 4 theory, which is not quite quasi-free, but it's almost quasi-free. And the non-quasi-freeness is basically that all the expectations where the number of A stars and the number of A's do not match, that this vanishes. Okay, so are there any questions concerning this slide here?
Yes.
Yes, please.
So I do understand that particle number should be conserved, so the good approximation should have that property, but is it easy to understand that this GBC thing and the integration over Z does this job?
Yeah, so that's what I try to explain. Okay, so gamma commutes with the particle number operator if and only if all expectations of operators where you don't have the same number of A stars and A's vanish.
Yes.
Okay, now let's make one simple example. Let's compute the expectation of A0.
Oh, yeah.
Okay, the expectation of A0 is the integral of Z against that function here. But that function only depends on the absolute value of Z.
Yes.
So if I integrate over the complex plane, I have a phase, and no matter what the radial integration does, I get a 0 from the phase integration.
Yes. Yeah, I think I understood that part. So you're saying that this same argument applies to any operator that does not conserve.
Because so any A0 star gives you a Z bar.
Okay.
I mean a Z bar phase, not
Okay.
I mean, and any A gives you a Z, and if those numbers don't match, the phases integrate to 0.
Okay.
And also in H Bogoliubov, there are phases, and also these will cancel.
Yeah, right. So it's the H Bogoliubov. For example, if you compute the expectation of AP A minus P, this will also come with the phase Z squared, and also there you get the 0. So it's really, this is why the phases here are crucial. The phases here are crucial, and the phases here are crucial, and that they play together is also crucial.
Okay, thank you.
Let me ask one more question. So a simple-minded way of getting a state with particle number conservation is simply to project this onto the sector in which it has a fixed particle number, like your n.
Sure. This would
Does
be
it give basically the same result?
No. The point is, this is really grand canonical. If you do it in a canonical way, I think it would come out slightly differently.
Okay, thank you.
Okay, are there more questions on that slide? Okay, then I continue. So given this result, there are several consequences or things you can compute. So the first thing that we can compute, and that is, that was the wrong introduction. The point is, we can also compute the two-particle density matrix. This has not been computed before for such a model. So this is, I mean, it's interesting mathematically. It's also interesting physically, because here you see the non-quasi-freeness of the state. We need actually, I mean, to prove the first statement, we need our first new correlation inequality, but to prove this here, we need our second new correlation inequality as well. So getting this is quite a bit harder than getting the statement I showed you before, but it's based on that statement. So what do we get here? Just as an example, I mean, we can compute the 4-point correlation function or the two-particle density matrix. One interesting thing here to note is, for example, we can compute the variance of the number of particles in the condensate. And it's, if you remember, beta scaled as n to the minus 2/3. So this is on the scale n to the 5/3. It depends on the interaction between the particles. And the physics behind this is the following. So for the non-interacting gas, what you see in the condensed phase, the variance of the number of particles in the condensate is order n squared. So this is quite unphysical. So it basically means you have a contribution which is extremely broad, and it's just related to the fact that you have no interaction. If you have interaction, this behavior is not favorable. The interaction suppresses the fluctuations, and what you get is a new variance. It depends on the interaction between the particles. It doesn't depend on the expected number of particles in the condensate, surprisingly, and it's on order n to the 5/3. Okay, and here you also see, for example, if you compute this expectation here, you see, this pairing function from Bogoliubov theory. Your question was related to that. I mean, how is particle number conservation there? We have particle number conservation, but for those expectations that are particle number conserving, we see this alpha function, so this pairing function. And you see it in these two expectations down here. Okay, so this is still there. Okay. Now, what we can also do, what I found pretty interesting is, well, we can compute the precise limiting distribution for the number of particles in the condensate. So what we can do is, the number of particles in the condensate is a random variable, and its law is given by this here. Okay, so so A0 star, A0 is a self-adjoint guy. You can associate a random variable to it, and well, you can look at its distribution. And well, I already told you that we have BC, we have the BC phase transition. So the law of large numbers is this here. To leading order, the expectation is given by that of the ideal gas. So this is not changed by the interaction. Now, I told you already the variance of that random variable depends on the interaction. It's given by n divided by beta v hat of 0, and plus corrections, of course. So we have the expectation, we have the variance, so you can ask for the limiting distribution. So you can look at the normalized random variable, you subtract the expectation, you divide by square root the variance, and you ask, does that have a limit as n goes to infinity? And indeed it does. And we have actually 4 parameter regimes. So we see, depending on temperature, 4 different limiting distributions. And for example, in the condensed phase, it converges to a standard normal distribution. There's another transition point where we see a mixture of a Gaussian and an exponential distribution. If you go down, I mean, if you increase the temperature further, at some point you see an exponential distribution. And if you're fully in the non-condensed phase, you see a geometric distribution. And I should stress here, so this is something, I mean, we can control, even in the non-condensed phase, we have order 1 particles in the condensate, and we can still compute the limiting distribution. And this is, I mean, what I found surprising here is that goes way beyond what you can expect to get with coercivity of the free energy. So at some point, we also prove something for the free energy. So the proof is variational in nature, but it goes way beyond coercivity. And this should be contrasted to the 0 temperature case where this is not correct. So what we see is, I mean, we have a free energy expansion with a remainder. I don't even remember it. It's a bit smaller than n to the 2/3. So you would expect, well, making statements about order 1 particles with energy given by order 1 is not doable, but it is. And the point is, this is because of the correlation inequality. So we really exploit the fact that we are dealing with a Gibbs state. So we are working with a minimizer and not with an approximate minimizer. So that's really the crucial point here. We really use the equation of the minimizer, if you like. Okay. And how do we do that? Well, here's a statement. So here's a theorem that we prove. And well, maybe let's ignore that first part here, okay? Let's think of matrices. It works for self-adjoint operators. So A will be the Hamiltonian, B can be whatever it likes to be. It need not be bounded from above or below, but it needs to be bounded relative with respect to A, okay? But let's think about matrices from now on. So let's look at this state here, gamma t. For me, it's a perturbed Gibbs state. So I think of A as the Hamiltonian and B as a slight perturbation. So let's think of B as a one-body guy, the second quantization of a one-body operator. So we should be able to make statements about A and about A plus TB. That's the spirit here. We know A and we know ATB, that's cheap, but we want to get something non-cheap. So what we assume is we know that we assume that we know the expectation of B in the state gamma t, okay? Or we have a bound. And we have that for some range of t values. And then what we get is a bound for trace B squared gamma 0. So why is getting a bound for B squared hard? Well, B squared, if B is a one-body operator, B squared is a two-body operator. So this is usually hard to get. We cannot just perturb the interaction potential in order to do a Hellman-Feynman type argument or Griffith argument. This is very hard, but this is the replacement for that. So what we find is, so we assume this here, and we get that the trace B squared gamma 0 is bounded from above by eta x eta plus a commutator term. You could say, okay, that commutator term involves even more operators, so how is that going to be any better? Well, the point is the following. The Hamiltonian A has four creation and annihilation operators. So it's a two-body guy. If you commute it with a one-body guy, you get a two-body guy again. If you commute it another times with a one-body guy, it's a two-body guy again. So this is not worse than the Hamiltonian. But the interesting point is I have not included the beta factors. So I have two beta factors here, and I have three beta factors here because A and B will come with beta factors in applications. And beta factors are small in our setting, okay? So I have one more beta factor here than I have here, and because of that, the right-hand side is much better than the left-hand side. Oftentimes, it's even, we get what we have on the right-hand side also on the left-hand side, but with a smaller constant, we bring it to the other side and we get a bound, okay? This is the spirit how we are going to apply this. And so this greatly simplifies and generalizes a correlation inequality that appeared in the work of Levine, Nam, and Rouchery. So the point is, it's simpler because we have way less perturbation terms, and the proof is really simple. I can show it to you very briefly, but let me also mention we have a higher order version of that. So we don't just extend their theorem, we simplify it, but we also have something for higher order correlations, which we need for the two-particle density matrix. Okay, and now let me try to convince you in the last 2 minutes that I have that this is very natural. Okay, so first of all, there's one statement that we use to prove this, and that is what's called Stahl's theorem, or it's an infinite dimensional version of Stahl's theorem, but that's not the issue here. So what does Stahl's theorem tell us? Well, if you look at that perturb partition function here, that's a function of t, and the statement of Stahl's theorem is, and this is highly non-trivial, the statement is that zt is the Laplace transform of a positive measure. Okay, and so the measure has enough regularity to write down the integral. You don't have to worry about that. And the main point is now, this tells you something about derivatives. So think about differentiating that here with respect to t. You get a factor minus s down. So you multiply, you look at minus 1 to the power n, the nth derivative of ct. This is always positive. Okay, and that's an extremely strong property because it gives you convexity and or concavity, I mean, on all orders. So all derivatives are convex. And that is extremely helpful. Let me show you how we use it. So we use it in the following way. So we know our assumption is that the first derivative, so we have, well, the logarithmic derivative of zt is bounded. That means we can bound zt in terms of z0. Okay, this is a triviality. Now, if you differentiate the z of t twice, you get the Duhamel two-point function. That's almost like a second moment, but of course, it's not because there's non-commutativity. Okay? Now, the Duhamel two-point function can be related to the second moment via the Falk-Bruch inequality. And the Falk-Bruch is basically, this involves the second commutator. Okay, not so important for the moment. It just tells you, here's another simple step. If you can control the Duhamel two-point function, you can control the second moment. So how do you control the Duhamel two-point function? Well, you use Stahl's theorem. So the second derivative of the Duhamel two-point function, that's again a convex function because the fourth derivative does have a sign. So if you use convexity, you can just average. You can write the second derivative as at 0 as an integral over over the second derivatives on an interval. Well, then you use the fundamental theorem of calculus. You get back to the first derivative, but you have a bound for the first derivative. Okay, and so you get this bound here. Then you move the z0. Well, you get a bound, you have a bound for the first derivative in terms of z0. You move that to the other side, and well, you can replace the exponentials by the full states here. You can normalize them by partition functions. And that is, well, you have your input, you control the non-commutative second moment, you use Falk-Bruch, you come to the second moment, and you get that here. And this is the bound that I showed you. So it's an extremely simple proof. And just to compare, in the work of Levin, Roucherie, that took, I guess, 8 pages, because they used an approximate convexity of the second moment. The second moment, the true second moment, is approximately convex, while here, the non-commutative or the quantum second moment is indeed convex. All right. And my time is up, so let me conclude. What we have done, we have gotten an approximation of the Gibbs state and trace norm. We have computed the two-particle density matrix and various condensate distributions. We have 2 new abstract correlation inequalities. One is an extension of Levin-Roucherie. Another one is also for higher moments. I didn't display it because I didn't have time. We expect that this will find applications also in other problems. And well, one thing that I liked, just because it's nice to look at, is one of them is proved with an infinite dimensional version of Stahl's theorem. And that is not a main point, of course. All right, so that's it. So thank you very much for your attention.
So thank you very much. Are there questions, comments? You can also write them in the chat if you have problems with the sound, or you just unmute yourself.
Maybe I could start with something. I was just wondering, thanks for the wonderful talk, by the way. I was just wondering if any of these, in particular the correlation inequalities, could be extended beyond the mean field regime. So could you
No, this is abstract.
Yeah.
You know, this is abstract. So we prove it in the following setting. You have A self-adjoint. I mean, I mean, it's a little more general than that, but I state it like that here because it's easy to state. So A is self-adjoint, B is symmetric, B is relatively bounded with respect to A with a constant smaller than 1. Like that, you have Kato-Rellich, and I mean, they are self-adjoint on the same domain, which is actually what we need. We only need that they are self-adjoint on this, so that A plus TB is self-adjoint on the domain of A for T in -1, 1. This is what we need. And you need that the things you need trace class of the exponential. And then you get this here. So it's not tied to this model in any way.
Yeah. And does this have any interesting consequences for
I
this?
don't know. I would encourage you to look into it. I mean, I don't know yet.
Thank you.
And maybe I should mention, I mean, what is different for the second correlation inequality? The second correlation inequality has an operator that commutes with all the other guys, which will be the number operator in the end. And this is probably more applicable to particle number systems, where you have such a distinguished guy.
Other questions?
Yeah, can I ask a question about this slide, about this correlation inequality? So you have to assume this eta bound. So I still don't have any intuitive understanding of this, but this looks something non-trivial, right? So this is
it's non-trivial, yes and no. So you should see it the following way. A is going to be the Hamiltonian, and B is going to be something that changes the one-body part of the Hamiltonian. Okay, so this bound here we get from a Griffith or Hellman-Feynman argument. So that means you take your free energy, it depends on the parameter T, you get free energy bounds, you use the convexity to use these bounds to get a bound on the derivative with respect to T, which is this expectation. And this is something that is coercivity. Okay, so you prove bounds for the energy. Given the bounds for the energy and the convexity of the relevant quantity, you get a bound on the derivative. And so this is entirely convexity. The non-convex, it's like you need to control the energy with a perturbation term of the one-body guy, and that is something that is usually doable. This is why we like that. This is why we are not afraid of getting that. We are, however, afraid of getting that here because to get this, you would need to do a Hellman-Feynman. I mean, you would need to differentiate with respect to the interaction, and that is terrible. But you get this from that theorem, and it really, this is the step that goes beyond coercivity. So what we get here is true for the Gibbs state. It's not true for approximate minimizers of the free energy. I think that's the interesting part that we were also surprised by. I mean, I must say, I was very much surprised by the fact that we get something that goes beyond coercivity.
Thank you.
And maybe I also have a question, but it's more I'm trying to understand. So at the beginning, you define a beta critical.
Yeah.
And this beta critical, so the beta critical is 1 over n to the right. So the beta critical goes to 0 when n goes to infinity.
Yeah.
So the critical temperature goes to infinity.
No, okay. The point is the following. I mean, okay. I mean, it's very natural because in the thermodynamic limit, beta is of order 1, right? So where is the independence? Well, the point is, this is the ideal gas, okay? Already here, what you could do is just, so here is actually a row. The n is actually a row. If you let your box size go to infinity, this is the model you're familiar with.
So rho, you mean the density? Rho is the density.
Right. The density rho. We have side length 1. We could let the side length go to infinity in such a way with n that you have a row here. And the row would be order 1, the temperature would be order 1, and we could do that. The point is just the model has one free parameter. And we make a choice.
But so you could also say you send the volume to infinity and you fix because it's just that it's technically more convenient, or is it really equivalent?
No. I mean, it's literally the same. I mean, except for that formulas change. It's literally the same. We could let the volume go to infinity, and then there would be other n factors appearing here and there, and it's a choice of parameters. It's not a choice for the theorem. But I mean, one thing is clear. It's not a thermodynamic limit, right? I mean, one should make that distinction. So the point is, it's a joint. You can see it in the following way. You have the thermodynamic limit, right? That's the hardest system you can study.
Yeah.
And for example, that there are also dilute limits. You would take a thermodynamic limit first and then a dilute limit. But then you could combine the two into one. You get something simpler. Okay?
Okay.
This is also a combined limit. And it would rather be like, you could take the thermodynamic limit and then you do a high density limit. So you have many particles close together. This is a version of doing that in one step.
Okay.
So it's clearly simpler than the thermodynamic limit. I mean, that should be stressed. So it's what people call a mean field limit.
Yeah.
Mean field limit, or this model has also been named the weakly interacting Bose gas. People have called it like that as well. So you have order n particles interacting with order n particles. You have a macroscopic range of the interaction. You have a mean field parameter in front of the interaction. And very important, you still have a spectral gap of your Laplace. That's the crucial point. You have a spectral gap of your Laplace. This is why this model is tractable. I mean, for example,
go on. Sorry, go on. Yeah.
I mean, if we didn't have that, we wouldn't even be able to prove the existence of the BEC phase transition for the interacting model. So for no thermodynamic limit regime can we prove the BEC phase transition. If you were able to do that, you are famous, right? I mean, this is a problem and this is the same as proving magnetization for the Heisenberg ferromagnet in 3D. That's the same level of difficulty.
Okay, maybe are we out of time? So there is still time to ask us quick question, maybe. Maybe there are let's check other questions because
Can I ask a quick question? So what is a precise condition for the interaction? You only said that it's mean field, but
you mean technical? So it's
is there sort of large class of interactions that you can treat and all these theorems about?
Right. I didn't comment on that. So if you look at that Bogoliubov Hamiltonian here, need that V hat is non-negative. If not, that formula doesn't make sense. Okay. So what we assume is that V is non-negative, that V hat is non-negative, and we assume that V hat is summable against the absolute value of P. So these are...
So that's all?
That's all.
And
so, I mean, okay. So the assumption that V is non-negative, we can probably get rid of that. The paper is 102 pages, and I mean, if you assume V hat is non-negative, which is also natural, I mean, you don't expect to get around that. then V is non-negative is a minor issue. I mean, to be honest, I don't even know where I use it. Okay, I mean, probably we use it somewhere, but because we didn't kill it. But I mean, it may be worth thinking about it now that we talk about it. Yeah, but
Okay.
it's okay. There's a question in the chat. Thank you.
Yes,
What's
about the archiving number of the paper.
of the paper of Bose-Einstein condensation? Okay, okay, I can do it when the question, I mean, when we close the questions, I will answer to that then.
Are there more questions, comments, protests? Okay, no, okay, then I will close the official part of the seminar. So thank you very much again.
Thank you very much for having me.
And it was really a great talk. And I think we can stop the recording.